Stripping down science. The Naked Scientists.
Now, how can my voice here in Cambridge reach you at home? This week, we're exploring the science and the technology of radio broadcasting, finding out how a sound that originates in my throat gets captured, converted, and then beamed around the world.
We will also delve into digital radio to find out how it differs from FM, and we'll hear about a new breakthrough in gene therapy for irregular heartbeats.
Plus, have a listen to this.
This is Dave shouting very loudly at a capacitor-based microphone.
We've been making our own microphones to see how they work, and we'll show you how we did it very shortly.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
And this is The Naked Scientists with me, Chris Smith, and also with Ben Bousler.
Hello. If you would like to get in touch with us, you can tweet at Naked Scientists, you can comment at facebook.com/The Naked Scientists, or email chris at thenakedscientists.com.
Now, this week, the world celebrated Sound Engineers Day, but can you guess what day this was? Well, it was on 12/12/12, of course, or 12/12/12. Now, joking aside, behind the thousands of broadcasts that are happening all around the world at any one moment, there's an invisible army of engineers who make the whole process happen so that sound waves leaving a presenter's mouth can be captured, converted into electromagnetic signals, beamed through the air and then picked up by your radio so that you can listen. And to find out how, we're joined now by John Adamson, who's the BBC production editor for London and the South East, and he's known colloquially as the Digital Doctor. Hello, Doc.
Good evening to you.
Good evening, John. So did you celebrate Sound Engineers Day?
I was very busy at work, dashing back and forward between London and Tunbridge Wells, and unfortunately I missed that moment. I was hoping to catch 12/12/12, 12/12/12 on the screen, but a phone call came in and I missed it. Isn't that dreadful?
I intended to observe it too, but then I think something cropped up on the television, another form of broadcasting. So tell us, John, when I'm speaking, what actually is the journey between this studio where I'm sitting and a radio in someone's car or their living room?
Starting at the beginning, your voice generates mechanical vibrations that have to be picked up by something called a transducer. That would be a microphone, and that converts the mechanical energy into electrical energy. That tends to be an absolutely tiny signal at that point. So you can't do a great deal with that. You need to amplify it so it's usable. So the next thing you would find in the transmission chain is an amplifier that would boost the signal by probably around 70 decibels. So in the trade we work at 0 decibels as a standard sort of level for everything we do in broadcasting. That's just under a volt of audio. If you imagine a microphone produces minus 70 or thereabouts, this is brought up to 0. Then, of course, we'd want to do more than just broadcast a microphone, much as it's nice to hear your voice, of course. Probably other things you want to hear, like CDs, vinyl, maybe cassette, mini disc, MP3 players, things like that, to all sorts of audio reproducer systems in the chain these days. So they would be fed into an audio mixer. That's just a clever system of mixing what you want to hear and routing it to the transmitter. So you might have, in your studio, I imagine you probably have about 12 channels of mixing on your desk there, maybe slightly more.
So this is when people are saying mixers, what you are referring to are a desk with all these sliders on it that you can move up and down, and they change how loud any individual source is. Presumably they're basically varying the resistance, so the current has to flow through a bigger or smaller resistance to make it louder or softer.
That's exactly right, yes. If the fader is fully closed, it presents a short circuit to the input of the amplifying stage. If it's fully open, then all the signal that's coming in from the other side of the fader gets transferred across to the output stage. So you have a mixer, and that mixer might have some clever things like pre-fade channels on it, so that as a broadcaster you would want to hear the signal signal before you go live. You want to make sure it's working. It's at the right level. So in the case of bringing me up on your sound desk at the moment, you would have talked to me off air, checked on pre-fade that you were hearing me, and then when you're happy with it, you would open the fader, and then I would be routed to the transmission chain in the way that you are. So we have the audio mixer.
Now, what about the level, though, John? Because one of the things that we're all watching in a studio is how loud things are, how soft things are, and we're tweaking knobs and things to make sure that things don't get too loud or soft. But is there also work going on behind the scenes to make it sound very consistent? Because one of the things people notice when they're tuning into their radio in their car or at home is the sound level is always nice and consistent.
That's right. Well, in the early days, we didn't have any sort of processing other than a protection limiter on the end of the audio line feeding the transmitter. And that was all well and good. It stopped distortion because the transmitter circuits could only cope with a certain amount of level, plus 8 dBu is what we tend to use as the maximum level in the business. But the difficulty is that music in particular has quite a dynamic range. So you want to be able to compress that a bit, especially for people who are listening in less than ideal conditions. You know, people are either listening in their cars, or maybe they're listening in the kitchen and the kettle's boiling at the same time, or the vacuum cleaner is on. All these things may be happening, which make it difficult to cope with the wide dynamic range. So what we do is we process the signal, we compress it. And in the early days, it was a simple compressor, which might put in about 12 dBs of compression. So in other words, if anything above minus 4 dBu came in, that was compressed to be the same level. So
in other words, you're narrowing the gap between the loud bits and the soft bits, so you can make everything a lot louder, because it's the peak is not going to be super loud, but then the quietest bits are not super quiet either, so it's more consistent.
Indeed. Now, if you were to listen to perhaps Radio 3 on FM, they still broadcast a very wide dynamic range, whereas if you were listening to Radio 1, the other extreme, it has hardly any dynamic range at all.
And it sounds very loud, doesn't it, when you hear the relative difference between the radio stations?
Yes. Now, originally we just had compressors and compressor limiters in the chain, but now we have audio processors, and what they do is they chop up the audio spectrum from 30 hertz to 15 kilohertz into different frequency bands, and they individually compress all these. So that means you can make the sound even louder. Some people may remember the Phil Spector sound from the 60s, the wall of sound it was called, and that was that sort of principle where every part of the audio spectrum was squeezed to the absolute maximum, so you had this, as they called it, wall of sound. Very, very loud, very consistent, ideal for listening in less than ideal conditions.
Lots of people say they're very fatiguing to listen to. Just very briefly, yes. So once we actually get to the transmitter, most people listening to these programmes are probably going to be listening on FM. What, just briefly, is FM?
Two sorts of modulation systems that we've had for a great number of years, AM and FM. AM stands for amplitude modulation, FM stands for frequency modulation. So in the case of AM, amplitude modulation, the intensity of the transmitter signal is varied according to the amplitude of the audio. But in FM, it's the frequency of the transmission that's varied according to the amplitude of the audio. So in the FM system, Radio Cambridgeshire operates on 96 megahertz. The loudest passages would cause it to swing back and forward between 96.1 and a bit and 95.8 and a bit.
So actually, although you're tuned to 96, it's actually a little bit either side of the 96, which is wiggling in the spectrum, and that's what right. Your radio is picking up on.
Indeed, and that requires a clever decoder in the set that will allow you to do that. Unlike the days of AM, where you could just have something simple like a crystal set which could decode the AM signal, with FM you need a more elaborate detector.
And given that FM is stereo as well, does that mean you're actually broadcasting two sets of information, one corresponding to the right speaker, one corresponding to the left, and they're both wiggling around 96 megahertz? How are you doing that?
Well, that is true, but it's a bit more complicated than that, because if you go back to the history of FM, or VHF as we used to call it, back in 1955 when it was opened, we just had a mono signal. So all we were presenting to the transmitter was an audio signal from 30 hertz to 15 kilohertz, and that was mono. And then someone developed the stereo system. But of course you needed compatibility between the stereo system and the old mono system. So to transmit left and right would be a problem, because how would an old radio which didn't have a stereo decoder in it know what this signal was? So what we did is we developed a pilot tone system and continued to broadcast the mono signal between 0 and 15 kilohertz. But then we took the stereo information, the difference signal if you like, and added that to the FM signal, but stuck it on a subcarrier of 38 kilohertz, which meant that if you had an old mono receiver, it didn't pick up that signal, it was quite happy. But if you had a stereo decoder, it would decode the 38 kilohertz subcarrier frequency information along with the mono signal, combine them together and bring it back to left and right.
Super. Thank you very much, John. And we'll explore the digital story, which gets even more complicated, in just a second. That's John Adamson. He's the BBC production editor for London and the South East.
Now, as we've already heard, the first, but in my opinion probably the most important part of any radio broadcast or recording is the ability to capture a voice. So we know that when we speak, vibrations in the voice box create a pressure wave in the air. This travels through to cause vibrations in your ear, and they are then converted into electrical signals and fed to the brain where they're decoded. But all the kit that we use for radio is electric, so we do need a device that converts that pressure wave into an electric current. And this is what a microphone does. So to find out how microphones do that, we asked our own Dave Ansell if he could build one from scratch. And to do that, he looked back into the history books.
Well, the first kind of microphone which was practically used was developed by Edison in the 1880s to work with a telephone. And that was based on having a little pot full of carbon granules. You apply a voltage across those carbon granules and you get a current out. Now, if you shake that using the sound wave, which is coming from your voice, that will change the resistance of those carbon granules, so that will change the current going through it, and you have an electrical signal. The problem is that the resulting electrical signal was horrible, and it produced a very, very bad rendition of the sound it was producing. But it was very cheap, and you didn't need an amplifier, so it was very useful in the early days.
How did people take those ideas and build on them?
So the next big improvement in microphones was done by a guy called Wenter, based in Bell Labs in 1916. And I'm going to build a model of that now. This is based on the principle of capacitance. I've got a piece of tin foil, and if you apply a voltage to that tin foil, some current will flow into it, a tiny, tiny amount, but a little tiny bit. And it might become negatively charged. Now, if you have applied the opposite voltage to the second piece of tin foil, then that will become positively charged. And for a certain voltage, a certain amount of charge will flow from one plate to the other. So we say the system has a certain capacitance.
But if you allow those two bits of tinfoil to touch, then presumably the current will just flow from one to the other, and instead of having a way of storing energy, a capacitor, what you've got is just a very poor circuit.
That's right. So we don't want to do that. So I'm going to separate these two pieces of tinfoil with a piece of cling film, which is a really good insulator.
So what we now have is a very basic model of the standard electrical component, which is a capacitor that's capable of storing a small amount of charge. But that still doesn't look to me like it can collect sound from the environment and turn it into an electrical signal.
Well, the way it does this is a property of capacitors. Now, this is because if you get the two plates, a positive plate and a negative plate, very close to each other, they sort of stabilise each other. The positive plate attracts the electrons of the negative plate, and so the voltage you need to push them in gets lower, so you can get more charge on for the same voltage, and we say it has a higher capacitance. And the closer those two plates are together, the higher the capacitance is. So if the plates move backwards and forwards, the capacitance is going to change up and down.
So in order to turn this into a microphone, we need to find a way of changing the distance between the two. Is that as simple as shouting at it, essentially? We put a vibration in it from our voice, that changes the distance between the two plates, and that gives us a model of that sound wave in a changing electrical current.
That's what I intend to do, yes. Shouting is going to be involved. As the sound waves hit it, they're going to move the plates together and apart. The capacitance is going to change, so the amount of charge on those plates is going to change, so you get a current flowing in and out, which you should be able to detect as an electrical signal.
So we're wiring up our two pieces of tinfoil and a piece of cling film now, I'd be amazed if it does work. Dave, over to you. What's next?
We've now got this connected up to a recorder, so we should be able to listen to it later. I'll give it a go. I might speak quite loudly because my experience is this isn't the most sensitive microphone in the world, but let's give it a go.
OK, hold on. I had better stand back if Dave's going to be shouting. Dave's voice is loud at the best of times. Off you go then, Dave.
So I'm now shouting very loudly at this capacitor-based microphone.
Let's have a listen and see what it sounded like.
So I'm now shouting very loudly at this capacitor-based microphone.
Well, that is noisy, and your voice was quite quiet, despite you shouting very, very loudly. But it worked, so clearly this demonstrates the principle. But why was it so noisy?
One of the problems is that my microphone is also actually quite a good aerial, and it will pick up any electrical interference going on in the room. So to improve this, we'd probably want to put it in a sort of metal tub and earth the outside of that metal tub to give it a bit of protection against the electric fields moving about. If you build this really well, it produces a decent microphone. Though in 1931, the same guy, Mr. Wenter, who seems to have invented most microphones in the world, developed a slightly different technology for microphones called the dynamic microphone, which we can actually have a go at building one over here.
So a dynamic microphone, if I remember rightly, is the type that you'll see most singers using on stage. How does it differ?
So this has got to do the same thing as the capacitor-based microphone. It's got to take a vibration from the air and turn it into an electrical signal, but it's doing that conversion differently. Now, this works on the principle called electromagnetic induction, and you may have done this at school. All you need to do is take a coil of wire, which I've got here, and if you take a strong magnet and wave it near the coil of wire, you generate a voltage.
How do you capture the sound wave and make it wave a magnet next to a coil?
Essentially, you've got to turn the movement of air into a movement of a physical object, and a good way of doing that is to essentially make a drum skin, because that can be easily moved by the air. So I've got a drum skin here, and if you just feel that with your finger, and I talk into it, you can feel the vibration.
Yes, so I can feel the vibration in my finger. What we've basically got here is a plastic tub with a bit of balloon rubber stretched across the top. So that's a good way to collect that vibration. And then how do we put that into a magnet that goes into the coil?
We've got to somehow attach either the magnet or the coil to this and keep the other one of them still. I've connected the magnet to it. All you need to do now is get a coil and wire it up to your recording device.
So again, I'm going to step back a bit, I think. And Dave, if you could shout at your dynamic microphone.
So this should hopefully be recording something marginally useful. And it's basically just shouting at a magnet on a drum skin.
And now let's have a listen back.
So this should hopefully be recording something marginally useful. And it's basically just shouting a magnet on a drum skin.
So again, very noisy, but it's clearly you, and I can pretty much understand what you're saying there. Now, microphones come in all different shapes and sizes, and from the tiny little lapel ones through to the big fluffy ones that they use for recording people on film sets. Are they all based on the same technology?
Most microphones are now based on the development of the capacitor, or they're called condenser microphone. And there are some more exotic types of microphone. You get strange kind of piezoelectric microphones based on the same principles as your gas lighter, which are the clicky gas lighters. And basically, if you can think of a way of converting vibration into an electrical signal, someone's probably tried to make a microphone using it.
Dave Ansell showing me how to make a microphone with things he found lying around the house.
You're listening to The Naked Scientists with Chris Smith and with Ben Valsler. Now, if you have any questions or comments for us, then do please get in touch. You can tweet at Naked Scientists. You can also comment on facebook.com/The Naked Scientists or email us, chris@thenakedscientists.com. Still to come, we'll be going digital in a minute. We'll be exploring the pros and cons of DAB, that's digital radio. But before that, let's find out what's been hitting the science headlines this week. Ben, what have you got for us?
Well, normal heart cells can be converted into specialised pacemaker cells using gene therapy, and this could pave the way to building a biological pacemaker, according to research published in the journal Nature Biotechnology. A heartbeat originates from a small region of the heart known as the sinoatrial node, which contains a very small number of specialised cells which act as the pacemaker. There are actually fewer than 10,000 of these cells in a typical adult heart, whereas the heart itself may contain around 10 billion other cells. They function by initiating an electrical signal that creates each heartbeat in a very smooth and coordinated way. But if they are injured by disease or through ageing, then the heartbeat can become irregular. This can stop the heart from being able to pump blood properly, and the only currently available treatment is to fit an expensive electronic device known as an artificial pacemaker. But for the last decade, research has been ongoing to find a biological alternative. Now, Nidhi Kapoor and colleagues at the Cedars-Sinai Heart Institute in Los Angeles, California, report that they've been able to convert adult rat heart muscle cells, these are called cardiomyocytes, into pacemaker cells using a gene therapy technique. They first of all examined a number of candidate genes, all known to be expressed during embryonic development of the heart, and they settled on a gene called TBX18. And when this was loaded into an adenovirus vector and expressed in adult cardiomyocytes, they become faithful replicas of pacemaker cells, and they function in exactly the right way. In fact, further tests confirmed that they operate the same clock mechanism, they respond to external stimuli in the same way, and they even take on the small size and characteristic shape of natural pacemaker cells. And this was the case both in the dish and in animal models of heart disease. Furthermore, they even retain this function after the gene stops being expressed, so you don't need to go back and treat it again. So they've now called these cells ISAN, or induced sinoatrial node cells, and they suggest that in the near future we could grow a clump of these cells before transplanting them into a heart, or we could simply inject a gene therapy agent directly into a patient's heart and do away with the need for artificial pacemakers.
Amazing. So from ISAN to ICAN, if you can make it work. Thank you very much. Now, also this week, scientists have uncovered residues of 7,000-year-old cheese. Chemist Professor Richard Evershed from the University of Bristol is one of the authors of a paper in the journal Nature this week, which describes how he and his team have made this rather milky discovery. Hello, Richard.
Hello there.
So how did this story begin?
It began truly about 30 years ago when one of our co-authors, Peter Bogucki, was putting together evidence from some sites he'd been excavating with colleagues in Poland, where they'd been uncovering these perforated ceramic potsherds. And he propounded a theory based upon those potsherds that they were basically cheese strainers, and basically started to develop the idea that these early farmers, which is the linear band ceramic culture, were dairy farmers.
When you say they were perforated pots, we're talking clay pots with fairly substantial holes drilled in them, rather like a top of a pepper pot.
Holes, but very numerous holes. If you look at the images that are in the article, they're all over the vessels. They look like a sort of small colander.
And obviously one can say, well, they look like the kind of thing that modern day people use to strain cheese, but just because they look like it doesn't mean they definitely were being used to strain cheese. Is there anything else they could have been used for?
Well, that's right. And in fact, we've had an interest in identifying dairy products from the archaeological record for a number of years. And these vessels were one of the major sources of sort of typological evidence. But I must admit, I'd been rather sceptical. And I'd often said in my lectures, but surely these could have been used for straining anything.
So how did you approach dealing with this and trying to find out what they really were used for?
Well,
how did you discover cheese?
Yeah, this is where the two studies sort of collide. Our research, in one part, is looking at the origins of dairying by looking at pottery vessels, usually cooking vessels. We developed a methodology, a chemical method, which allows us to identify milk fat, and it's based upon the fact that animal fats, which are the most common type of organic residue that you find in archaeological pottery when you study pottery from Europe, can be identified through their fatty acid signatures based upon studies that we've done studying many modern animals, carcass fats from dairy fats, pigs, horses can all be separated. So we can quite confidently identify different fats. So if we go into archaeological pottery, recover the residual fats in there, we can identify these fats quite unambiguously as to whether they're dairy fats or or carcass fats. And
but these pieces of pottery have been in the ground in this site in Poland, in the centre of Poland, for 7,000 plus
it's
years.
Remarkable, isn't it? Yes.
And you can get fats out of them that were from the cheese or the dairy products these people were working with.
Absolutely. It never ceases to amaze me, but it's due to the fact that these fats are preserved deep within the fabric of the pottery, and I imagine that they go into sort of molecular-sized pores in this aluminosilicate sort of matrix where they're protected from, say, bacteria getting in there to degrade them, and in the right sort of soil types, they're protected from leaching from out of the pottery by groundwater.
So you got specimens of the pots, you took small samples which enabled you to isolate these fats. What do those fats tell us then? They say that there was dairy material in these pots.
That's right, and just to clarify, we're not only focusing on the cheese strainer vessels, we've looked at a large number of other vessel types from the site, and quite specifically what it shows is that these perforated vessels, these putative cheese strainers, are the ones that contain dairy fats. If you then sort of start to put together this as like a forensic exercise, we've got dairy fats associated with perforated vessels, and you start to ask yourself the question, what other milk processing activity could you reasonably have been doing which required you to strain some sort of milk product? Well, it's cheese making. There is no other milk processing activity that uses a straining activity.
Why do you think these people wanted to make cheese?
Well, there's obviously two motivations. One, you would be producing, if you had a substantial dairy herd, as the animal bone assemblages from these sites seem to suggest, you would have had surplus of milk at certain times of year in the summertime, for instance. And so the production of cheese would have been a way of producing a non-perishable product that you could then preserve throughout the year, so you could take full advantage of the nutritional properties of milk in the wintertime. But the other critical factor, and this is where Peter Bogucki comes back into the story with his paper from the 1980s, it relates to this lactose intolerance phenomena. It's very likely, almost certainly, that these early farmers were lactose intolerant, so they would potentially have got quite poorly had they been drinking substantial amounts of whole milk. So it looks like that this straining activity was perhaps a recognition of this, and they had found a way of getting round the lactose intolerance problem, because what you're doing when you separate the curds from the whey contains the lactose. So you're actually producing a lactose-reduced product when you produce cheese, and thus lactose-intolerant farmers would have been able to exploit the nutritional qualities of milk.
Richard, thank you very much. One has to wonder what that cheese would have tasted like back 7,000 years ago. Professor Richard Evershed from the University of Bristol. Now, something that caught my eye this week is the question of jellyfish, and Australia, in line with its reputation for being home to some of the world's most venomous creatures, also is home to one of the world's most dangerous jellyfish, if not the most dangerous organism, the box jellyfish, Chironex fleckeri, after Flecker, the man who is credited with having caught one and induced it to sting him to prove that it is a really very nasty jellyfish. This kills people, both around the Queensland coast, but also its relatives in Malaysia and also around the Philippines, maybe hundreds of deaths a year. And the thing is, we don't really know why. We just know it's very poisonous. And a group of researchers now writing in PLOS ONE, this is Angel Yanagihara and Ralph Shohei, they've actually shed much more light on this week in their paper. First, what they've done is to come up with a very good way of producing concentrated versions of this venom. They got tentacles from Chironex fleckeri and another species of box jellyfish. They isolate the nematocysts. These are the little miniature jellyfish hypodermics that are loaded with the venom, which discharge on contact with skin and pierce the skin, pushing the venom in. They spin these things down, and then they use centrifugation to rupture them, releasing the venom proteins, which they're then able to skim off. And they used samples of blood from human donors, but then also animals, to inject this material or add it to cells to see what the effects were. And what they find in samples of red blood cells, and then also in experimental animals, is that the venom appears to trigger the cells to rupture and release their potassium. And when they made some careful microscopic images, they show that the proteins in the venom assemble into little pores that then punch holes in the cell's membranes. And this is why the cells release potassium into the bloodstream, which is normally stored inside cells. And it's this potassium that they think kills people, because when you have large amounts of potassium in the bloodstream, what it does is depolarizes the membranes of electrically active tissue. heart cells and nerve cells, in fact every cell in the body, has a voltage across its membrane which is produced by pumping potassium into the cell and excluding sodium. And so if you let all of the potassium come out of the cell, you lose the voltage across the membrane, and the cell normally uses this voltage to do important jobs in the cell. So if it's not there, the cell dies. And they think that this is what happens. And in their experimental animals, their hearts just stopped when the potassium level went up. So then they said, well, is there anything we can do to stop this? And they started just testing random chemicals they had in the lab, and they tested a chemical called zinc gluconate, which is a solubilized form of zinc. It's a zinc salt, and they found it could very potently inhibit the venom. It seems to stop it assembling into these miniature pores that punch holes in cells, as long as there's lots of zinc there. And even better, it's very cheap. And amazingly, it's even better at doing what it does than the anti-venom, which you can obtain from hospitals and things, but which is often administered too late anyway. Zinc, very easy to get hold of, very easy to administer, and as long as you keep pumping it in, it seems to stop the toxin. They also suggest that perhaps rubbing this onto the skin, if you have some zinc-containing cream, may also stop more of the nematocysts from discharging, and therefore it could potentially also limit the dose of the venom into people. So a very cheap way of mitigating against something that probably kills hundreds of people a year.
So does that mean that if you have a very high zinc diet, or you take lots of supplements containing zinc, then you'll be protected in some way from the effect of the sting?
Unfortunately, I don't think so, because they did effectively try that experiment, because they, in some of their animals, gave the zinc and then gave the venom. And in others, they gave the venom and then gave the zinc. And they found that the latter, giving the zinc after envenomation, was more effective. And they think that the reason is that the zinc doesn't stay in the bloodstream at a high enough level for long enough to inactivate the venom. Whereas if you have given the zinc afterwards, then every time it meets a poison molecule, it effectively deactivates it. Now, one thing they do say, though, given that they're saying about rubbing on the cream onto the skin, sun cream has got a lot of zinc oxide in it, so it may be that really slapping on the sun cream might be beneficial too.
Excellent. And now from solving a problem that's caused by an animal to getting an animal to solve a problem for you. It turns out that the quills of the North American porcupine might help us to design better medical needles. Porcupine quills can penetrate skin better than a hypodermic needle because of tiny backwards-facing barbs at their tips, and these render the quills very difficult to pull back out. And this trick now could inspire better medical equipment, such as better needles and better tissue adhesives. These are North American porcupines that we're talking about. They have 30,000 of these spines on their body, and they're known to be an effective defence mechanism. They penetrate in very easily, they're often very difficult to remove. And their quills, these spines, are unlike those found on the African porcupine, and they're unlike those found on our hedgehog, because they have these microscopic barbs on their tips that point backwards away from the quill. And these barbs intrigued researchers, including Dr. Jeffrey Karp from the Brigham and Women's Hospital in Boston. So they undertook a series of experiments to see what effect the barbs had. They published their results in the journal PNAS, and what they did was get a sample of pig skin from a local butcher and see how much force it took to push one of these quills in and then to pull it back out. They then repeated the tests after they'd sanded off these barbs and with other things, including a hypodermic needle of the same diameter. The really surprising thing was that the presence of the barbs actually made it easier to penetrate the muscle. So a hypodermic needle takes around 0.59 newtons of force to pierce into pig flesh, but the barbed quill required only 0.33 newtons to achieve the same task. They then took samples from the skin, looked at them under a microscope, and actually the barbed quill showed a much smoother puncture site. That suggests that the skin absorbed less energy and took less damage. And they're now arguing that these barbs are a bit like the serrations on a serrated knife. What they do is concentrate areas of force, which means you don't need to deform the skin as much in order to cut into it. And they say that if we actually copy this barbed structure, then we could make smaller, finer needles that won't buckle, and a range of other biomedical applications.
Research at the sharp end. Thank you, Ben. Now, meanwhile, in a galaxy far, far away, mysterious objects have been blasting out super bright X-ray bursts towards the Earth. The only galactic objects that are brighter than these are supermassive black holes that exist in the centres of galaxies. And so far, we've not been able to work out what these really bright objects, known as ultra-luminous X-ray sources, actually are. But now, Durham University's Dr. Tim Roberts and his colleagues have finally shed some light on what these things could be.
There's a long-standing mystery in X-ray astronomy, which is the nature of these objects called ultraluminous X-ray sources. They're the brightest X-ray sources we see in other galaxies outside of the central X-ray source we see in some galaxies, which is a big, what we call a supermassive black hole. We've thought for a while that there are other black holes, smaller black holes, but the real mystery is how big they are, whether they are similar to some black holes we see in our own galaxy that are roughly the size of our sun, or whether they're something in between, something we call an intermediate mass black hole. And so what we do when we look at ultraluminous X-ray sources is we're trying to discover the size of the black holes.
How does looking at the X-ray sources actually tell you how big the black holes are?
There's a very useful physical property of black holes that gives us an indication of how big they might be, and that's simply how bright they are. It turns out that there's this thing called the Eddington limit, which really is, if you like, a maximum brightness that they can reach for a given mass, for a given size of black hole.
Why do they pump out these X-rays?
You get X-rays from black holes. It's basically actually the best way of finding a black hole is to look for this characteristic X-ray emission. You get that when a black hole feeds, when a black hole, what we call accretes material from something else. Now, in some black holes, that's just the accretion of gas, just free gas that floats in space. Generally, that's how you see these supermassive black holes at the center of galaxies. But in certain cases, for the smaller black holes, occasionally you find them orbiting another star. So it's like a binary star system where one of the stars is a black hole. And in those systems, occasionally they're close enough that the black hole can actually pull gas off the outer surface of the star. And that's when you see them. The gas falls into the intense gravity field of the black hole and gains energy. It gets spun round and round the black hole quicker and quicker, and as it does so, it gets hot. It gets so hot that it literally glows in X-rays as it approaches the edge of the black hole, and that's really how we see it.
So this one that you're documenting in Nature, how did you spot it?
Well, with the satellites we have at the moment, with the big X-ray observatory missions, there are some objects they tend to look at quite frequently. One of those objects is the Andromeda Galaxy. That's because a lot of the X-ray sources you see in neighbouring galaxies are what we call transient. They only turn on for short periods of time. They turn on and then they very quickly turn off again. So we have these programs where we're monitoring the Andromeda Galaxy fairly regularly to look for sources that come on and then fade and go off again. This is one of those sources.
Andromeda's about, 3 million light years away?
2 to 3 million, yeah.
And when you made these observations, what did you actually see?
Well, we saw a source that we hadn't seen before that had turned on. We looked again a couple of weeks later, and it had got brighter, and over the next few days it brightened further until it got up to a luminosity in the units we use of about 10 to the 39 ergs a second. Now that's interesting because that is the Eddington limit for a stellar mass black hole, one that's roughly the size of our sun.
And what did this tell you?
We saw this incredibly luminous outburst of radio emission. Even more extraordinary, the radio emission seemed to be changing very rapidly. It was fading away pretty rapidly as we were watching it. That was in combination with a very slow decay of the X-ray emission. Now, that's interesting to us because we've seen very similar behavior in sources in our own galaxy when they're at their brightest. And the great thing about the sources in our own galaxy is we know how big the black holes are. The black holes, again, are these stellar mass black holes, these ones that are, of the same order, slightly bigger, but of the same order than our own sun. What that means is that this ultraluminous X-ray source is coming from a stellar mass black hole. And that's really interesting to us because it tells us that, by extension, a lot of these other mysterious ultraluminous X-ray sources we're seeing in other galaxies potentially are stellar mass black holes. And that's the mystery we've been trying to solve for a long time.
Tim Roberts from Durham University discussing the results he published this week in the journal Nature. And as usual, you can find all of our news on our site at thenakedscientist.com/news.
And you can hear a longer version of that interview, along with discovering a new satellite for testing tech and finding out how to tackle the growing problem of space junk, in the latest Naked Astronomy podcast online at nakedscientist.com/astronomy. And now it's time for our Planet Earth section. And the flat farmland area in the east of England, known as the Fens, isn't everyone's cup of tea. But the rich, peaty soil is of particular interest to climate scientists. Now a team from the University of Leicester have developed an experiment in the centre of a field to measure how much carbon is absorbed and released by this peaty soil. Planet Earth's Richard Hollingham went to see the experiment, where he spoke to Ross Morrison and first the head of the project, Heiko Balzter.
We are trying to get to the bottom of the carbon emissions that are coming off these soils under different conditions, both different land use conditions and extreme weather as well. We've had very extreme dry conditions last year, lasting until about Easter. And this year, of course, has been one of the wettest summers, I think, in the last 100 years in Britain. So we are trying to find out what that does to the carbon exchange between the land surface and the atmosphere. And the carbon emissions coming off the peatlands here, of course, contribute to the global warming problem. So there is the feedback between the land and the climate system, and we are trying to get numbers of emissions that are coming off the ground.
Now, Ross, you're responsible for the experiment here, which is cordoned off behind a barbed wire fence. It's a series of solar panels, I'm guessing, for electricity. There is a substantial, almost like a fridge-sized green box, and then a very peculiar... I don't know how best to describe this. It's obviously some sort of weather instrument, but it looks like a weather instrument crossed with a whisk. What is it?
This is a weather station, but quite an advanced weather station. It's got all the elements you'd expect from a normal weather station. For example, we're measuring temperature, relative humidity, radiation and that sort of thing. But then the bit that looks a bit like a whisk is the more advanced part of this. What we have here is a device, an anemometer, that basically measures atmospheric turbulence. And then we have the other device, which basically measures the concentration of CO2 and water vapour in the atmosphere.
And you're measuring the carbon dioxide, coming off the peat and going into the peat? The exchange between the exchange of gases?
At certain times of year, plants take up carbon dioxide from the atmosphere. And throughout the year, soils basically lose carbon dioxide to the atmosphere. And so essentially, using this instrument, we can basically calculate how much is moving over a very quite high frequency. Sort of every half an hour we get a measurement from this. And then obviously over longer periods of time we can build that up to get an idea of how much carbon we're gaining at certain times of the year and then losing at other times of the year, and then kind of the balance over time between that.
So when there's a crop in the field, spring, summer, then you'd expect the carbon dioxide to be coming into the peat, and this time of year you'd expect the carbon dioxide to be leaving.
Yes, at the moment there is there's a vegetation cover, but this is just coming back naturally. So this is natural.
It's just sort of nettles and weeds and bits and pieces.
Yes.
Yeah.
When the crop is actually growing, it does accumulate quite a lot of carbon. At least the crop we measured this year, which was iceberg lettuce, did on some parts of the growing season actually result in a net removal of carbon dioxide from the atmosphere as the crop was maturing. And then at other times of year, following ploughing and this sort of stuff, at this time of year when essentially most of the soil is bare, we'd be expecting to see a net loss of carbon to the atmosphere.
Heiko, this isn't the only setup you've got. You're looking at other sites as well.
That's right. We have 3 towers in total in the Fens now. One is operated by the Centre for Ecology and Hydrology, and 2 are operated by the University of Leicester. They are covering a land use gradient with 3 different types of land use. One is in the semi-natural fen in Wicken Fen, which is one of the few remaining areas of pristine peatland in the Fens. The second one is on a restored area, that is Baker's Fen, near Wicken, that is now managed by the National Trust for nature conservation purposes and is trying to re-wet the soil that was previously used for agriculture. And this third one that we set up this year is the first one that is on agricultural soil on farmland.
And how will the information from this be used? I mean, what do you want to do with it?
Well, it has huge implications for knowing exactly the amount of greenhouse gases that is emitted from these land surface areas. First of all, because we need to understand the Earth system fully, and we need to know how important the greenhouse gas emissions are from this area to assess how important it is to protect the carbon that is locked in the soils here. Secondly, there is, of course, an implication for the farm managers in the sense that we are trying to identify the best way of actually helping them to reduce and control their carbon emissions, which is in their own interest. And this is one of the motivations why this farm manager here has made the land for us available to install the instrumentation.
Heiko Bolster and Ross Morrison from the University of Leicester talking to Richard Hollingham. And you can hear more about that project in the Planet Earth podcast, which you can find on our website at thenakedscientists.com/Planet Earth.
You're listening to The Naked Scientists with Chris Smith and with Ben Valsler. If you have any questions or comments for us, then do get in touch. Tweet at Naked Scientists, comment at facebook.com/TheNakedScientists, or email us, chris@thenakedscientists.com.
Now let's return to our topic this week, the science and technology of broadcasting. If you're not currently listening online, then you could be using one of 3 different ways to receive your radio. We've already heard about AM and FM, but now there's also DAB, that's digital audio broadcast. The BBC first started broadcasting digital radio back in 1995, and now most of their output can be found on a DAB radio. But if FM was working, then why go digital? Still with us is John Adamson. He's the BBC production editor for London and the South East, and as we said earlier, the digital doctor. So, John, why did we want to go digital?
I suppose it was a combination of quality and quantity. So enhanced listener choice and better quality, particularly in marginal signal conditions. If we go back to AM just very briefly, medium wave and long wave, there's another radio station every 9 kilohertz apart. So the audio bandwidth is only 4.5 kilohertz. Barely better than telephone quality, not very good at all. Also, a finite number of frequencies that cannot be reused very often because the transmissions spill over a very wide area. They can't be very well targeted. In the case of long wave, there's only 15 channels for the whole of Europe. So you can imagine that's quite difficult to manage that frequency spectrum effectively. Medium wave has rather more, but it's still 4.5 kilohertz audio bandwidth to avoid interference to adjacent stations. Aerials are rather large, not a lot of choice there, really. Also, medium wave has the problem of after dark interference, strange noises in the background, continental interference, whistles and whines and buzzes in the background. FM made things a lot better, of course, because we got the stereo, as we said earlier, and more immunity to electrical interference. Also, because it was on the VHF band at around about 3 meters wavelength, aerials were a sensible size, so you could target your audience quite effectively. So in the case of BBC Radio Cambridgeshire, they've got a transmitter at Madingley that's targeted just for the environment around there. Why did we go to DAB? Well, FM still had a problem in marginal areas where there's something called multipath interference. I don't know if you've noticed this, if you're driving along or using a portable radio, that sometimes you get all sorts of hisses and burbles and squeaks and things. That's multipath interference. And that's a function of analogue radio, really, that if you get a wanted signal and a reflected signal, which inherently must be delayed with respect to the original, it will interfere. If you think of analogue television that was shut down just last year, you may remember seeing ghosting on the picture. What that is the visual equivalent of the interference you would get on audio. So the reflected signal always causes a problem to the main. DAB offered something rather new, and that was that because of the modulation system used and the coding systems used, you could have a number of transmitters all working on the same frequency. So, for example, the BBC National Digital Multiplex operates on one frequency right around the country. All the transmitters work together, and although some of them will be delayed with respect to others, if they're within a certain window of timing, certain delay, they will add, and the listener won't get any interference. High quality audio is possible as well. Thanks to digital audio encoding, MPEG compression, that allowed us to squeeze more audio into a given bit of spectrum. If you were using linear digital audio, you would need round about 1.5 megabits or 1.5 megahertz with a space for one stereo audio channel. That's not very efficient. But with MPEG, this allowed us to reduce that to, say, 256 kilobits, and that was alleged to give you round about CD quality. So in the early days, what we were thinking of with DAB was we'd have more channels, but not many more, but high quality and a more rugged, reliable transmission system.
OK, so if we come back to the audio compression in a minute, because I think we need to point out that that's different from the type of compression we were talking about before. When we were talking about amplitude modulation and frequency modulation, that's essentially building a model of the sound of that pressure wave in the amplitude modulation. But with digital radio, you're not doing that, are you? It's not a direct model of the sound. It's differently encoded.
Yes, it's all digitally sampled with a load of ones and zeros, effectively, and it all gets assembled back in the decoder again. So if you were to listen to DAB radio spectrum on an analog set, all you would hear is a load of random noise.
And how does the signal change with this? Because I have a digital radio at home, and it seems to be, ironically, digital. It's either perfect and sounds beautiful, or the signal is dreadful. Whereas with an FM radio, I can tune it, and it sort of seems to fade out. The quality fades out. Is digital always as good as it's going to be, or not present?
The theory is that you either get a perfect signal or you get no signal at all. But in reality, there's that grey area where the signal isn't quite strong enough for your set's decoder to make sense of. So what you get is this characteristic sound which has been described as bubbling mud. The difficulty with that is a really irritating sound. With FM, you just get more and more noise as the signal gets weaker, or you might get these burbles that I mentioned to you earlier, and squeaks sort of sounds with multipath distortion. But with the digital burbling mud sound, it's really quite difficult to follow the program. So it's not perfect. Because of the modulation and coding system that's used, it's generally better for mobile and portable reception. So if you're driving low in your car, it should be more rugged than an FM equivalent. And of course, you're on the same frequency, so you're not having to retune every few miles as you find a different transmitter.
Well, thank you very much, John. That is John Adamson. He's the BBC production editor for London and the South East.
Now, you're listening to The Naked Scientist, and we're talking with John Adamson. He is the digital doctor, so we can call him Dr. John Adamson. We've got lots of questions coming in. Lots of people, including Graham in Norwich, and also we've got an anonymous text here as well. The big disadvantage of DAB is the delay. So can you comment on how we get the timing right for the pips, for example, because they're clearly a bit behind, and the delay that's intrinsic to digital, please?
Right. Well, there's no magic answer to this one, because as there's so much intelligence going on in the audio coding system, in order to compress it to 256 or less, and in fact the DAB standard for most stations now is 128 kilobits, there's a lot of sampling of the audio to begin with to analyse how much can we throw away and still make it an acceptable signal. That takes time at the transmission end, but also it takes time at the decoding end, where your set's got to understand what's going on there. So fundamentally, DAB is going to be behind analogue in the same way as digital television is behind analogue television.
Now, that was talking about the file compression, where we're making the file smaller, as it were, in order to broadcast a better quality one. Going back to what we were talking about earlier with audio compression, Gerald McMullen on Facebook asks, why is it that some stations become tiring to listen to after even a short period of time? And he points out that his daughter can happily listen to Radio 1 for hours, but he can't listen to it for very long at all.
It's all to do with the amount of compression and the type of compression that is put into the signal. As I said earlier, audio processors nowadays are very clever devices, multi-band devices, so they chop up the audio spectrum into different chunks and they process them separately. And you can put an amount of basic compression in, and you can add clipping. Clipping in moderation is fine because it adds intelligibility. In fact, the old telephone system used to have lots and lots of clipping on it, which made it nice and easy for people to understand what was being said, even on a really crackly, horrible line.
This is where, if you've got a wave, you're literally just chopping the top off the wave, isn't it, to make it a bit quieter?
Exactly that. Now, that in moderation is fine, but it can be quite tiring after quite a short period of time. Normally around about 5 to 10 minutes, some people start to notice the clipping effects in the audio processing that's used. And unfortunately, a lot of broadcasters, when they put the audio compression in, do it for an instantaneous reaction to listeners who perhaps are just tuning down the dial. They find their radio station and they think, wow, that's loud, that's very impressive, I'm going to hang on in there for a bit. That's all well and good, but very quickly this fatiguing effect can take over, and it affects some people more than others. And that's a strange thing, that you might find one person doesn't notice the fatiguing effects, but other people find it really, really distracting and disturbing and want to tune away very quickly.
Thank you very much, John Adamson. He's the BBC production editor for London and the South East, and known as the Digital Doctor. He answered a lot more questions for you, which we've actually published as a special edition podcast. If you go to nakedscientist.com/specials or look us up on iTunes, the specials feed, you can find the additional podcast with all of the extra questions about digital and analogue radio answered there.
And now, speaking of questions, Hannah Critchlow gets charged up and switched on for our question of the week.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
This week, we wonder what links potato, soap and skin.
Hello, Naked Scientist. Martin here from Norwich. We have a touch lamp on our desk that goes on or off when you touch it. I accidentally touched the lamp with a piece of soap in my hand, and the lamp went off. My question is, what is so special about soap that you can use it to turn the lamp on or off? We also tried other materials, and we found out that it works with potatoes as well. Thank you.
So why are touch-sensitive switches so sensitive to skin, soap and potato, but not everything else? We asked Philip Garced, PhD electrical engineer student at Cambridge University, for the science behind this home experiment.
This effect is all to do with the fact that our bodies, along with many other things, are able to store a certain amount of electrical charge. If you've ever had a static electric shock, you'll already have some experience of that. And how much electrical charge something can store is known as capacitance. In a touch lamp, when an object that can store charge, like your hand, comes close to the sensor circuit, it will influence the circuit's behaviour, and usually this will cause a change in either a voltage or the speed of a timer circuit, and if that change is big enough, then the lamp will switch on or off. But it isn't just you that can store charge, loads of other things can. That includes soap, fruit, vegetables, fizzy drinks in bottles. As long as it can store enough charge to fool the sensor into thinking that there's a hand there, then it'll probably work. On the other hand, materials like paper, plastic and wood, they don't generally really store electrical charge, so they're unlikely to work. The technology used in touch lamps is very similar to that that's used in smartphone touchscreens. The sensors do vary a little bit in sensitivity and design though, so in some cases you'll need to hold the bar of soap or piece of veg directly with your hand for it to work, but in other cases just its presence near the sensor will be enough. Why not have an experiment to see what else you can get to work? I found it really funny that I could scroll through my emails on my phone using a tangerine from the fruit basket.
So it turns out that anything that can conduct electricity, like the inside of a tangerine, and also block electricity, like the tangerine skin, can act as a capacitor and store charge. Simply putting this capacitor near a touch-sensitive gadget, like Martin's lamp, is enough to switch it on or off. Sticking with the subject of science at home, Thomas Kammerturns from Berlin got in touch searching for an explanation for this.
Dear Naked Scientists, I wonder why the texture of chewing gum changes if you do heavy physical exercise or drink coffee while chewing.
So what could be affecting chewing gum to change its texture and taste? Send us your thoughts by posting on our Naked Scientists Facebook page. You can email Chris at thenakedscientists.com. You can join in our live debate on our forum, which is at nakedscientists.com/forum, or you can tweet at Naked Scientists.
That was Hannah Critchlow.
And that is all we have time for this week. Thank you to our guest this week, John Adamson, and also to Richard Evershed. Thank you for joining us at home, and do please join us next time for our Christmas special, when we'll be answering your Christmas-focused questions. Send them in to chris@thenakedscientist.com. And if you're looking for Christmas presents, don't forget we have a new book out, my new book, Everyday Life Under the Microscope. Big title, The Naked Scientist. Got a picture of an ant with a lemon for a bottom. You can find out why if you read the book. That's available from all good bookshops and at Amazon. In the meantime, Merry Christmas and see you next time. Bye-bye.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.